Hello students, welcome to Interconnecting Physics. Today I will explain you how to solve the numerical problems related to combination of capacitors. In last video we have studied the basic part of combination of capacitors. In this video we will study the complex numerical problems based upon the combination of capacitors. So without wasting time, let's get started. For regular updates you can follow me on given links. So first of all, there are some basic steps to solve the problem. Number one, read carefully what the problem is, because most of the students run away. It's not the solution. The solution is read carefully what the problem is. Number two, find the concept, theory or principle behind that problem. Okay. Now number three, recall the formula that we use to solve the problem. Then write down the given values with proper units. Suppose you are given with capacitance of capacitor, you are given with potential difference between the two terminals, or you are given with some current. So write down all the given values with proper units. Then convert all the values in same system of units. If you want to solve the problem in SI system, convert all the quantities in SI system of units. If you want to solve the problem in CGS, then convert accordingly. But most of the time we solve problems generally in SI system. Now solve the problem, because these are the basic steps. If you follow these steps, the numerical problems will be very easy for you and you will build confidence with the numerical exercises. But if you run away, then in life you can never be able to solve the numerical problems. Okay. Now today we are going to solve the numerical exercises based upon the combination of capacitors, that is capacitors in series, capacitors in parallel. Okay, capacitor in series or capacitors in parallel. So let's see what type of formulas we are going to use. When n capacitors are in series, then we use the formula 1 over C equivalent equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus up to so on 1 over Cn. And for if we have two capacitors, then 1 over Cq equal to 1 over C1 plus 1 over C2. Take LCM and you get the result. If you have two capacitors in series, then result will be C equivalent equal to C1 C1 C2 divided by C1 plus C2. If we have n capacitors in parallel, then C equivalent equal to C1 plus C2 plus C3 up to so on Cn, means in parallel combination we just add all the values. When n capacitors each having capacitance C, suppose the value of all the capacitors is same, that is C. Okay, then if they are in series, we divide the capacitance by number of capacitors, and if they are in parallel, then we multiply the capacitance with the number of the capacitors. So these are the formulas which we have already studied in last video. Okay, now there are some important points to remember such problems. Number one, in series combination of capacitors, charge remains same and voltage gets divided. Suppose if we have three capacitors in series, okay, right plate of capacitor is connected to the left plate of the another capacitor, then they are said to be in series and they are connected to some battery. Okay, then we know that charge remains same across each capacitor and voltage gets divided. Suppose V1, V2 and V3. Okay, if we have parallel combination of capacitors, then voltage remains same. Okay, parallel combination means left plates are connected to one terminal and right plates are connected to one terminal of the battery. Okay, like this. Then they are said to be in parallel, and in this voltage remains same, but charge gets divided because here at this point we have three diversions, number 1, number 2, number 3. So Q1, Q2, Q3. So in series charge remains same, in parallel charge gets divided. In series voltage gets divided, in parallel combination voltage remains same. Okay, now let's solve the problems. Numerical number 1, it's very easy. If C equal to 1 microfarad, then what will be the equivalent capacitance between A and B? Suppose we have three capacitors and each having value 1 microfarad, 1 microfarad, 1 microfarad and 1 microfarad. And we have to calculate the equivalent capacitance between point A and point B. You see here, capacitor 1 and capacitor 2 are in series. Okay, and what is the formula for series? If you have two capacitors in series, this is C into C divided by C plus C. Let us denote this by C1. Okay, then C square divided by 2C. C cancels out with C and result is C divided by 2. The result of this will be C1 equal to C by 2. Now the equivalent diagram will be this C1, because this has been solved now, and another is this C. Point A, point B. Now these two are in parallel. Okay. So in parallel we just add the capacitances. So C equivalent will be C by 2 because its value is C by 2 plus C. Okay. It's 3C by 2 and answer is 1.5 microfarad. Okay. Now numerical number 2. You see we have 4 capacitors and value 3 microfarad, 3 microfarad, 4.5 microfarad and 4.5 microfarad. Let us say this is point A, this is point B. Okay. Now these two capacitors are in parallel, and you know when two capacitors are in parallel, result is C1 plus C2. So answer is 9 microfarad, and the equivalent diagram will be like this. Okay, A, B. This is 3 microfarad, and this has been calculated, and the result is 9 microfarad, and this is 3 microfarad. So now these are in series, and we know series is 1 over C equivalent 1 over 3 plus 1 over 9 plus 1 over 3, which is equal to, if we take LCM, which is equal to 7 over 9. If 1 over C equivalent is 7 over 9, then C equivalent equal to 9 divided by 7, and answer is 1.29 microfarad. Now the problem number 3, and very important, and it is called as wire connection problem. Okay, wire connection. Okay, now I will tell you the method how to solve such type of problems. Now, calculate the equivalent capacitance between point A and point B of the network shown in the figure. Given C1 is 2 microfarad, C2 is 4 microfarad, and C3 is 6 microfarad. Okay. So let's solve this. Now it's very difficult to judge here which of the capacitance is in series and which of the capacitance in parallel. Most of the time students make mistake and they think that these three capacitors are in series, but this is not like that. Okay, let us understand the method. Suppose this is at positive potential and this is at negative potential. Let us say, okay, this is the method. You can assume it positive or it as 0, but generally we assume it as positive and it as negative. Okay. Now, suppose we have connected here some false pattern. Okay. Suppose point A is connected to positive terminal of the battery and point B is connected to negative terminal of the battery. This is fictitious pattern. Fictitious means false pattern. Okay. Now you see here, from here to here, there is no element present over here. It means at this distance, there will be no potential drop and the point A will be same as that of this point. Means at this point, the potential will be same, that is A, which is positive. Okay, because there is no element present over here, so that the potential drop occurs. Okay, so there is no potential drop, so it means point A will come here. Now from here to here, again there is no element present over here, no capacitor, no resistor, not any element. It means no potential drop across here. So it means point A will come here. It means these 3 points, 1, 1, this and this, these are at same potential. Okay. Now start from B. From B to this point, there is no potential drop because no element is present over here. So point B comes here. Now from this to this place, again point B comes here because there is no element present over here, so that potential drop occurs. So there is no potential drop, so point B will come here. Now from here to here, capacitor C3 is present. Capacitor C3 is present. It means there will be potential drop and this point is A, means different potential. You see, different potential. Okay, let us understand again. Let this A is at positive potential and let this B is at negative potential. And these 2 points are connected to some false pattern. Okay. Okay. Now, from this to this, point A will come here because there is no element present over here and there will be no potential drop. Now, from this to this, again there will be no element present here, so there will be no potential drop. Again point A comes here. Now from this to this, you see here Potential drop occurs because C1 capacitor is present over here. So there will be potential drop. And this point is attached basically with this B point. Okay. So here is point B. Okay. If this is B, there is no element present over here. So B will come here. Now from this point to this point, you see capacitor is present over here. There will be potential drop. And this is A. This is, if this is B, then this will be A. You see, there is no capacitor present over here, so point A will come here, and there is no capacitor present over here, so point B will come here. Okay. Now let us draw the equivalent diagram. Between point A and B, capacitor C1 is present. Okay, C1 is present. Between B and A, capacitor C2 is present. Capacitor C2 is present. Between A and B, capacitor C3 is present. Capacitor C3 is present. It means these three capacitors are in parallel to each other. Okay, these three capacitors are parallel to each other because from A to B, these three has same potential difference from A to B. Okay, you see here from A to B C1, from B to A again C2, from A to B C3. So these capacitors are parallel to each other, and in parallel combination we just add the values, and result will be, if this is 2 microfarad, this is 4 microfarad, and this is 6 microfarad, then answer will be 12 microfarad. Okay. Let us understand this by taking some another problem. Suppose we have two capacitors A, B points. Okay, here one more capacitor present, and here one more capacitor present. Okay, now start from here to here. Okay, again let us say these 2 points are connected to some fictitious pattern. Okay, plus minus. So this is at positive potential and this is at negative potential, mean both are at different potential. Okay, now if we start from this point to this point, then A will come here because there is no element present over here. Now when we move from here to here, we see there is one capacitor present here. Earlier we assumed that no capacitor was present over here, but now this time capacitor is present over here. That means potential drop will be there. Potential drop will be there. So let us assume this point is X, because potential drop and X will be at some different potential. Okay. Now from A to X, again capacitor is present, so it means potential drop will be there and this point will be X. Now start from B. If we move from here to here, there is no element present over here, so point B will come here. Okay. Now from here to here, there is one capacitor, so potential drop will be here, and there will be potential drop, and point X is here. Okay, and when we move from B to X, you see again capacitor is present here, so it means there will be potential drop, and we consider this single point as X. Okay, now let us draw equivalent diagram. Now from A to X, there are two capacitors. From A to X, 1, this is A, this is X, 1 and 2. Okay. From X to B, again there are two capacitors. Okay. Now these two are parallel. If C, 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 these two are parallel, so answer is 2C. These two are also parallel, so answer is 2C, and equivalent diagram will be, these two will be in series, and answer is 2C multiplied by 2C divided by 2C plus 2C, which is 4C square divided by 4C. This cancels out with this cancels out with this, and answer is C. Okay, so this is the method by which we can solve these wire connection problem. Okay, number one, we assume one point at positive potential and we assume another point at negative potential because we assume some fictitious battery between these 2 points. Okay, then if some element is present over here, some element like capacitor, if some element like capacitor is present, then there will be potential drop. There will be potential drop, and we consider that point say X. Okay, if there is no element present over there, then it means there is no potential drop and the same point will come on the second position. Okay, so by this method we can solve the problems. Now next, find the equivalent capacitance between A and B. Okay, between A and B. Take C2 10 microfarad. Okay, C1, C3, C4, C5 4 microfarad. Okay, so again let us say that this point A is at positive potential and this point B as negative potential because they are connected to some fictitious pattern. Okay. Now from here to here there is no potential drop across here, so point A will come here. Okay. Let us move through this path. We see C4 capacitor is present over here, so there will be potential drop across C4. That means point A will not come and there will be some another point, let us say X. Okay, because there will be potential drop across C4. Okay. Now from this to this again C1 is present, there will be potential drop. Let us say this point as Y. Okay. Now from Y to this again potential drop occurs here because C5 is present over here, some element is present over here. So then this point will be, let us say if this point is B, then there is no potential drop, this point B will come here. Now from B to Y, obviously from B to Y there is some capacitor, that is C5, so there will be potential drop across C5, so point Y here and point B here. Okay. Now from B to this again capacitor C3 is present, so potential drop will be there and here point B and there will be some another point, that is X. We have already assumed this point as X. Okay. So now equivalent diagram from A to X, from A to X it is C4. Okay, it is C4. From A to Y it is C1. From A to Y it is C. Okay, from A to X it is C4. From A to Y it is C1. Now from Y to X it is C2. From Y to X it is C2. Now from X to B it is C3 and from Y to B it is C5. You also draw in your copy this diagram. Okay, only then you will be able to solve it. Okay, so again from A to X capacitor C4 here, from A to Y capacitor C1 here, from X to Y or Y to X capacitor C2 is here. Okay, C2. From X to B capacitor C3 is here and from Y to B capacitor C5 is here. Now this is called as Wheatstone bridge. These type of diagram we generally called as Wheatstone bridge. In chapter 3, that is current electricity, we will understand Wheatstone bridge in detail. But till now, let us understand the principle of Wheatstone bridge. If C4 divided by C1, if C4 divided by C1 is equal to C3 divided by C5, okay, then the potential at point X will be equal to potential at point Y. Okay, again I repeat, if this divided by this and this divided by this, if both are equal, both having same value, then potential at X will be potential at Y. Okay, if potential at X will be equal to potential at Y, then we can ignore this C2. We can ignore this C2 because here potential is V, here potential is V, no potential difference, potential is same. So there will be no flow of charge from X to Y or from Y to X. That means we can ignore C2. Okay, and this is called as balanced Wheatstone bridge. When we call Wheatstone bridge as balanced, when potential at X will be equal to potential at Y, and when we ignore C2, we can say that it is called as balanced Wheatstone bridge. Let us see C4 by C1. What is the value of C4? 4 microfarad. What is the value of C1? 4 microfarad. What is the value of C3? 4 microfarad. And what is the value of C5? 4 microfarad. It means left hand side is equal to right hand side. That means point X and point Y is at same potential and we can ignore C2. Okay, then equivalent diagram will be. These C4 and C3 are in series. Why? Suppose here charge Q starts to move. Then there will be two directions. One is this, one is this. Let us say Q1 is going along this direction, Q2 is going along this direction. Here is Q1, here is Q1. So in series combination charge remains same. In series combination charge remains same. So these C4 and C3 are in series, okay, and these C1 and C5 are in series. And also remember always the upper arms are always in series and lower arms are always in series in case of Wheatstone bridge. Okay. Now C4 and C3 is in series. So let us calculate the value. So C34 and C15. You see C15, and we use the formula C equivalent C1 C2 divided by C1 plus C2 if we have two capacitors in series. Okay, so let us use this 1 over C15 equal to 1 over C1 plus 1 over C5. C1 is 4 microfarad, C5 is 4 microfarad, so LCM is 4. So 2 by 4 it is 1 by 2, and if 1 over C15 is 1 by 2, then C15 is 2 microfarad, and again this is C3 into C4, this is C3 plus C4, which is equal to 4 microfarad into 4 microfarad divided by 4 plus 4, which is 16 divided by 8, and answer is 2 microfarad. Means C34 is 2 microfarad, C15 is microfarad. So equivalent diagram is 2 microfarad, 2 microfarad. Now these are parallel to each other. Okay. This has been calculated. This has been calculated. Both are parallel to each other. Both are parallel to each other, and in parallel combination we just add the values and get the result. And the C equivalent here is 4 microfarad. Okay. Hope you understand. Now let us move further. Numerical number 5. A network of 4 10 microfarad capacitor is connected to some 500 volt supply as shown in the figure. Determine number A, the equivalent capacitance of the network, and number 2, the charge on each capacitor. So let us understand this. So see this network. Now you see here 500 volt battery. Obviously let us draw this. This is positive, this is negative. Let us say from here some charge will start moving. But at the point A, we have two directions, number 1, number 2. Let us say capital Q charge moves along this direction and small q charge moves along this direction. Okay. Now, this Q charge will be here, this Q charge will be here because there is no diversion in their path, and this Q charge will be here. So these C1, C2 and C3 are in series because there is no change in charge. There is no change in charge. Again at point D there will be diversion. Okay, so this C4 is parallel to these combinations. It means C1, C2 and C3 are in series. In series the result will be 1 over C1, 2, 3, 1 over C1 plus 1 over C2 plus 1 over C3. Put the value, and the value is 10 by 3 microfarad. Okay, now when we draw the equivalent diagram we see 10 by 3 microfarad is parallel to this C4, and they are connected to some 500 volt battery. Okay, now these two are parallel. In parallel combination we just add the values. So 10 by 3 plus 10 equal to 40 by 3, and answer is 13.3 microfarad. So first question has been solved, that is equivalent capacitance, which is 13 by 3 microfarad. Now charge on each capacitor. Now we know that in series combination charge remains same. Okay. Now C1, C2, C3 are in series. So it means the charge on these three will be same, and C4 is parallel. So there will be some different charge present over C4. So let us calculate the charge on C1, C2 and C3, that is Q, which is equal to CV. Okay. And C equivalent multiplied by 500. What is C equivalent for series? It is 10 by 3, 500. Okay. So this will be charge on C1, C2, C3, and over C4 it is Q equal to C into V. What is C equivalent for C4? Which is 10 microfarad. What is C? 10 microfarad into 500. So here answer is 5 into 10 raised to power minus 3 coulomb, and the answer for C1, C2, C3 is 1.7 into 10 raised to power minus 3 coulomb. Okay. Now numerical number 6. Suppose we have 3 capacitors in series and the left plate of C1 is connected at 90 volt potential and the one plate of C3 is earthed. This plate is earthed. Earth means zero potential. Earth means zero potential. Okay. Now what is the question? What is the potential difference between the plate C2? That means we have to calculate the potential V2 across C2. Okay, these three capacitors are in series. Now we know that in series combination charge remains same. Okay, but potential gets divided. Okay, let us say potential across this is V1, this is V2 and this is V3. Okay, and what is potential? V equal to Q divided by C. So first of all we should have C equivalent and then we should have charge on each capacitor. Okay, so let us calculate C equivalent. So 1 over C equivalent, 1 over C1 plus 1 over C2 plus 1 over C3. So first is 20 microfarad, second is 30 microfarad and third is 15 microfarad. When we take LCM and calculate, the result is 20 divided by 3 microfarad. Okay, now what is the charge? You know, in series combination charge remains same. What is charge? Charge is Q equal to C into V. We have calculated C. What is V? 90 minus 0. Total potential from A to E is 90 minus 0, which is 90. Okay, this is and 600 microcoulomb. 600 microcoulomb will be charge present on each capacitor. Why each capacitor? Because in series combination charge remains same. Okay. Now let us calculate potential across C2. Okay. So V equal to Q divided by C2. Q is 600 microcoulomb and C2 is 30 microfarad. So answer is 20 volt. Okay. Now numerical number 7. We are given with some circuit and let us calculate equivalent capacitance between point A and B. Here we are given with some Wheatstone bridge. And what is the condition for Wheatstone bridge? If 18 divided by 9 is equal to 9 divided by 4.5, then potential at this point will be equal to potential at this point. 3 microfarad can be ignored. Okay. So let us see this. 9 1 is 9, 9 2 is 18. And this is 90 divided by 45, 45 1 is 45, 45 2 is 90. So 2 equal to 2. That means this is the balanced Wheatstone bridge. Balanced Wheatstone bridge. Okay, that means the potential at this point and potential at this point is equal and no charge will flow from here to here or here to here. So 3 microcoulomb can be ignored and the equivalent diagram is these two are in series. So 18 microfarad, 9 microfarad. These two are in series, that is 9 microfarad and 4.5 microfarad. So let us calculate if these two are in series. Let us calculate equivalent capacitance, which is 6 microfarad. Let us calculate equivalent capacitance, which is 3 microfarad. Now these two 6 microfarad and 3 microfarad are in parallel. So result is 6 microfarad plus 3 microfarad equal to 9 microfarad. Okay. Now again all capacitors used in the diagram are identical. Okay. C, all are C. Then calculate the effective or equivalent capacitance between point A and B. Again this is the problem of wire connection problem. Okay. So from here to here, let us assume there is some fictitious battery present over here. A is connected to positive terminal of the battery, B is connected to negative terminal of the battery, and A is present at positive potential and B is present at negative potential. Okay. So from here to here there is no potential drop, no element is present. So A will come here. Okay. From here to here again A will come here because there is no potential drop across this line. Okay. Now from here to here there is potential drop because capacitor is present. Let us say this point is X. Let us say this point is X. Okay. Now from here to here again capacitor is present. So here we have already assumed A. So there are two different potentials X and A because there is potential drop across this capacitor. Now from here to here no element is present, so there is no potential drop and X will come here. From here to here again there is no element present over here, so there will be no potential drop and X will come further here. Okay. Now from A to X element is present, so potential drop. Now from B, if there is no element present over here, B will come here, and at this line there is no element, so B will come here. So all the points are designated. Okay. Now equivalent diagram will be from A to X. From A to X, this. Okay. From X to A, again capacitor, this. X to A, this capacitor. From A to X, this capacitor, this capacitor. You also draw with me, okay? Now, from X to B. From X to B, this capacitor, this capacitor. From B to X, this is the capacitor, here is the capacitor. From X to B, this is the capacitor, here is the capacitor. Means first three are in parallel, next three are in parallel, and these two groups are in series. These capacitors are in parallel, C. The equivalent capacitance is 3C. If these three are parallel to each other, the equivalent capacitance is 3. Okay, then equivalent diagram will be 3C, A and B. These are in series, and the series when we calculate we get 1.5 C is the answer. Okay. Hope you understand this. Okay. The one way to understand is just take your copy, take your pen and draw with me, try to solve with me. Okay. Let us understand next problem 9. In the arrangement of capacitors shown in this diagram, if each capacitor is 9 microfarad, then what will be the effective capacitance between point A and B? Okay. Let us again understand. This is also the problem based upon wire connection. If this is point B, then this will be B. Why? Because there is no element present over here. There will be no potential drop. And here to here, again point B will come here because there is no element present over here. There will be no potential drop. Okay. Now from here to here, there is potential drop. Let us say this point as N. Now from point A, here, no potential drop. So point A will come here. And from here to here, element is present, capacitor is present, so there will be potential drop, and we have already assumed this point as N. Okay, so let us draw the diagram. From B to N, one capacitor, from B to N, third capacitor, C1, C3. Okay, so B to N, C1, B to N, C1, B to N, C3, B to N, C3, N to A, C2, N to A, C2, and A to B, C4, A to B, C4. Again, let us repeat. From B to N, C1, from B to N, C3, from N to A, C2, from N to A, C2, from A to B, C4. Okay. Now, these C1 and C3 are parallel. So, answer is just add these two values, and each value is 9 microfarad. So, it is 18 microfarad, and the equivalent diagram is 18 microfarad. This C2, these two are in series. Now, in series, let us calculate equivalent capacitance, which is 6 microfarad. Now, this 6 microfarad and this C4 are parallel to each other, and this C4 is 9 microfarad. Okay. So 9 plus 6 is 15 microfarad is the equivalent capacitance of the whole circuit. Okay. Let us understand last and the most important problem, that is capacitance of infinite network, infinite ladder. Okay. It means we are given with infinite combination of capacitors, infinite. Suppose 1 lakh. Let us say. Okay. And what is the method to solve such problems? Let us understand. Step 1. Identify the repeating unit from infinite ladder. Repeating unit. Okay. 1 microfarad, 2 microfarad, 1 microfarad, 2 microfarad, 1 microfarad, 2 microfarad, 1 microfarad, 2 microfarad. It means the repeating unit is 1 microfarad and 2 microfarad. This unit is repeating again and again. Okay. Now, step number 2. Leave first unit, and assume capacitance of infinite circuit. This infinite circuit is X. Let us assume equivalent capacitance of this infinite ladder, this infinite network is X. Let us assume. Now, suppose we have 1 lakh capacitors in this infinite ladder, okay, and the equivalent capacitance is X. Now, if we add 2 microfarad or 1 microfarad in 1 lakh number of capacitors, then will it make any effect? No, it will make not any effect, because in 1 lakh capacitors, if you add 1 microfarad or 2 microfarad, it doesn't affect any of the equivalent capacitance. It means the whole of the circuit has equivalent capacitance X. Okay, the whole of the circuit has equivalent capacitance X. Okay, so follow these steps and let us now solve the problem. Now we have already assumed leave first unit, and let us assume the capacitance of whole of the infinite network is X. Okay, so leave first unit 2 microfarad as such, 1 microfarad as such, and this is X. Now these two 2 microfarad and X microfarad are in series. How? Because let us say some charge starts moving from here. So here will be two directions. Some charge will go here, some charge will go here. So here will be same charge will flow. Here the same charge will flow. Okay. So these 2 microfarad and X are in series. Okay. So let us calculate equivalent capacitance. Let us denote this by C1. So 1 over C1 equal to 1 over 2, because first one is 2 microfarad and second one is X. So 1 over X, take LCM, and answer is C1 equal to 2X divided by 2 plus X. Okay. Now this circuit has been solved and answer is C1. Okay. Now this C1 and 1 microfarad are in parallel. So let us calculate parallel. Now we have already assumed the X is the equivalent capacitance of the whole infinite ladder. Okay. So X will be 1 microfarad plus C1. Hope you understand? No? Let us understand again. So first of all, try to identify the repeating unit. We know 2 microfarad, 1 microfarad is the repeating unit. Leave 1 unit and assume the equivalent capacitance of the infinite network is X. Let us see. Now, this is equivalent capacitance of infinite ladder. If we add 2 microfarad or 1 microfarad in this X, this will make no effect. That means if we take this equivalent capacitance as X, or if we take the equivalent capacitance of the whole of the circuit, it will remain as X. Okay. Now leave 2 microfarad as such, 1 microfarad as such, and write the infinite ladder, the equivalent capacitance of infinite ladder as X. Now these two are in series. Calculate these values, and after calculating we see the equivalent capacitance of this and this are in parallel. Now let us calculate the equivalent capacitance of the whole circuit. We have already assumed the whole circuit has equivalent capacitance is X. So X equal to C1 plus 1. 1 is here and C1 has value 2X over 2 plus X. Okay. When we calculate this, when we cross multiply, add or subtract, we get this will form a quadratic equation. Let us solve quadratic equation. X square minus 2X plus X. Okay. Minus 2. Take X common, we will left with X minus 2. Take 1 common, X minus 2. So X minus 2 into X plus 1 is 0. So we have two values of X, that is 2 and minus 1. But negative value of capacitance is not possible. So X equal to 2 microfarad. So what was X? It was the equivalent capacitance, of the network. Okay. So the answer is 2 microfarad. Okay. So hope you understand each and every problem. Today we studied wire connection problem, okay, in which we assumed the point A is connected to some positive terminal of the battery and B is connected to some negative terminal of the battery. And if there is any potential across the capacitor, then we write that point as X. And if there is no potential drop across any capacitor, if there is no element present over here, then A will move like same. Okay. Then number 2 we studied Wheatstone bridge. Okay, and we saw that if this is the shape of Wheatstone bridge, okay, then if this divided by this, if C1 divided by C2 is equal to C3 divided by C4, then this capacitance will be ignored and we take simple circuit as C1, C3 are in series and then C2, C4 are in series. Okay. Then third one we have studied infinite network. Okay. Hope you understand with this. If you have any problem, you can follow me on my Telegram channel or you can ask me in my comment section. If you want PDF notes, you can also ask me in comment section or you can follow me on my Telegram channel. Thank you very much. Don't forget to like, share and subscribe. Stay happy, stay healthy.